y'all ready? Yeah? Okay. So remember that K stands for the equilibrium of constant. And the expression, we take the products over the reactants, and we raise the concentration or the partial pressure to the power that its coefficient is. So whatever its coefficient is, that is the power to that. So it is important to note this. We do not have to be concerned about units for equilibrium constants because they're going to be very complicated, and it's just in general, you just forget about the units. So whenever you have to solve for it, you don't need a unit on it, just leave it blank and it will be fine. Or if they did really want you to have a unit, then the question might say in, and then it will tell you what it will be. So, but overall, just don't worry about those units. Equilibrium constant. So this example, we want to do what we can. If we don't want to, we don't have to. This is just plugging in information at equilibrium concentration to solve for K, the equilibrium constant. Now, we can do it if you want to, but it's very similar to what we did for example 2. The difference is example 2, we were just solving for the reaction quotient, Q, but it's the same process where you set it up, products over reactants, and then plug it in and solve. So would you guys like to do this one, or do you feel like you have a good handle on that? Do it? Okay. So the equation that it's talking about for the synthesis of ammonia, that is, if we look back at example 2, that's what example 2's equation was actually. It's just there. Where it is N2 plus 3H2, and then the products are 2NH3. The NH3 is ammonia. Okay. So we want to find the value of K at 127. The equilibrium constant is temperature dependent. So you will probably be told temperatures in problems, but for our purposes, it doesn't really matter. You just have to know that it is temperature dependent. So it could change at a different temperature. Okay. So I think I have room here. Yeah. So just so that we know how to plug it in, products over reactants. So the concentration of NH3 raised to the second power, because there's a coefficient of 2 in front of the NH3, over the concentration of N2 times the concentration of H2 cubed. So that's the way that we'll plug in these numbers to solve it correctly. And we're not solving for a Q because we were told their equilibrium concentration. So that's why we just know it's already K. Okay. So then we got 3.1 times 10 to the negative 2 squared over 8.5 times 10 to the negative 1 times 3.1 times 10 to the negative 3 cubed. And when solving out, just be very careful with your exponents and your scientific notation and all that stuff. If you feel like you're going to get confused with the scientific notation, you can always take it out of it before you plug it in. I got 37,950.7. Okay, and then since all of these numbers are given with 2 significant digits, then we probably would just go 3.8 times 10, 4, 10 to the 4. Okay. Okay. So anytime it asks you to solve for K and you are given like the concentration values for all the stuff, and you just plug it in this sort of thing. This setup, we get this from what's called the law of mass action, which we talked about that last week. Okay, so again, no unit because it's a K. So this applies to most chemical systems and solutions and gas phases, how we set that up. Remember from last week, we don't include anything that's marked as a liquid or a solid because their concentrations don't change, just gases and solutions. So there are some corrections for concentrated aqueous solution and gases at high pressures, but that would just be given to you if you needed it. Okay. So now the table that I have there, I just have that to show you that the same reaction was tested 3 different times where the initial concentrations were given, but then even though after they initially started out with different amounts and then they got to equilibrium, the equilibrium concentrations for all 3 trials were able to produce the same exact K value. Okay. Now, like I said, this is the same reaction that we just solved our example number 5 for, but it must be at a different temperature because the K values that are given here are not the same K value that we saw for. So that just means that this is at a different temperature, but it doesn't say what temperature it is. So as long as it's at the same temperature, it doesn't matter what you plug in, you should be able to get the same equilibrium constant each time. Make sense? Okay. Occasionally, we did talk about Kp last week. Kp just means that it's the constant that's developed from pressures. Sometimes the Kp does not equal the K. Sometimes instead of just K, it's Kc for concentration. So if they're not equal, then we could use this equation right here, where the R is still, well, I guess still, I don't know. It's the R that we used with the PV equals nRT equation. So that's the 0.08206 for the R because we're dealing with pressure. And the temperature would have to be in Kelvin. So if it's given in Celsius, you just have to change it to Kelvin by adding 273. And then N is the difference in the sums of the coefficients for the reactants and products. So these LM, JK letters come from back on page 6, where those were the coefficients that became the subscripts, where these are supposed to be the products coefficients added together, and these are supposed to be the reactants coefficients added together. Okay, so it's still products minus reactants, but you have to just make sure that you add together the total products and add together the total reactants before you subtract. So that's why it's the difference in the sums, which really doesn't make a lot of sense, but that's that. So in this situation, maybe you'll have to solve for Kp, maybe you'll have to solve for K, but you'll be given probably a balanced equation that you would be able to use the coefficients to subtract for. Okay. So example 6 is all about it. So if Kp is found to be 1.9 times 10 to the third, 10 to the 3, calculate the value of K at 25 degrees Celsius for the following reaction. Okay, so our equation we want to use, notice how also R times T are both raised to the change in N, so you have to multiply those together before you raise it to the power, so just be careful with that. Sometimes people only raise the T and not the R, so that would give you the wrong answer. So the Kp is given to us. The 1.9 times 10 to the third is the Kp. So that means we're not going to solve for the Kp, we're actually going to solve for the regular K this time. So just make sure you plug in the right spot. Then R is always the same, right? That 0.08206 for us. Temperature is given as 25 degrees Celsius. And to switch that to Kelvin, you have 273.15. So that's 298.15 Kelvin. I'm sure. Okay. And then the last thing you have to do before you just plug in and solve is you need to figure out the change in N. So for the change in N, product minus reactant, looking at the total coefficients. Okay. So we only have one product, so that's just going to be 2. If we had another product, you'd have to add that together, but we don't. Minus, now I'm going to put it in parentheses so I know these are both my reactants. We got 2 in front of the NO, plus there's nothing there, so implied 1 in front of the Cl2. So really, we're going to take 2 minus 3 and get a negative 1 as the exponent for the change in N. Did I lose anybody there? We all good? Okay. So then now let's just plug in. So 1.9 times 10 to the third is equal to K times, now this is where you got to be careful, right? It's the R times the temperature in Kelvin. Both things multiplied first and then raised to the negative 1 power. Does anybody know, like mathematically, what we can do if it's to the negative 1? What does that mean? Yeah, so it's like the inverse. So what I did on my paper to help me figure it all out is I moved where I just kept K in the numerator, because that's being multiplied, and then put these 2 on the bottom. So that helps me visualize what to do next. If you find that that's helpful, can you do that? Okay. So then now that we've figured out that those 2 are in the denominator, we have to multiply them, and then that answer gets multiplied by our 1.9 times to the third. And then I got for K 46,975. Or 2 significant figures. 4.7 times 10 to the 4. Yeah. This negative 1 just means that you could take the inverse, like, because if it's a negative, then it goes on the bottom of the denominator. So that's,
So if it was like any negative number.
yeah. But, well, if it's negative 2, you put it on the bottom, but it still has to be squared.
Oh, yeah.
It's the negative part that makes it go on the bottom.
Okay.
Yeah. Yeah. So 7.5, we talk about what does it mean when you have a really, really big K or a really, really small K. So that's what 7.5 is about. But 7.4 is just relating how sometimes KP and K are not the same thing, or how you solve for K. So we've got half an hour class left. Would you guys like to keep going or call it for today and just take 5 and 6 section notes tomorrow? Do you homework today? Okay. All right, sounds good.
Or is any of them?